So as a brief aside, it was discovered in the late 40s, early 1950s, that there could potentially be a component of angular momentum due to basically the rotating parts of a jet engine. And this was due to the fact that some of those early aircraft, those early jet fighters, like the Super Sabre and the MiG-15, they had very heavy propulsion systems compared to the total weight of the aircraft, because of the material of the compressor blades. So it was found that the propulsion systems of those aircraft gave a component of angular momentum that was not considered in the conservation of angular momentum equations, and therefore a little modification, little ad hoc modification to the conservation of angular momentum equations was required to take into account these effects. Now, it's worth noting as well that this effect can cancel out if you have multiple engines, so an even number of engines where the blades of the propulsion system rotate in opposite directions. However, for an aircraft with an odd number of engines, typically one, right, there is a component of angular momentum due to the rotating components of the propulsion system that we can write as such. So we have components in the X, Y, and Z directions, and this has been written with respect to the Earth axis system initially. So basically that's just the sum of all of the moments of inertia and angular velocities about some axis. Now this axis, the R-axis, is basically the axis of rotation of the rotating part of the engine, right? So that will typically be the longitudinal axis through the center of the engine. So we may use those terms, or that like little modification, to return to our conservation of angular momentum equations and include an extra term to describe the rotor effects, right? So you remember this is what we had before, equals these moments on the right hand side, the aerodynamic and thrust moments, but now we have this extra term here which describes the angular momentum terms due to the rotating parts of the engine. However, as we just said, that this is with respect to the Earth axis system, so again we need to go ahead and write that in terms of the body axis system. So we use the same expression as we did before. So again, this just describes the rotation of the new vector field, and we can write h bar dot, which remember is the partial derivative of h bar with respect to t, as this thing, just using the definition of h, right? So one of the little assumption that we can make here is that if the propulsion system is rotating at a constant speed, so in a cruise for example, then the rotational speed is constant, which means the change in rotational speed is 0. So if omega bar dot is 0, then that tells us that h bar dot is 0. So this term disappears. So we're just left with this cross product, which we can calculate in the usual way, and therefore we can rewrite our modified conservation of angular momentum equations to include the rotor effects